Hello, and welcome to Math Calculations for Nurses. I'm Professor Don Rayella. In this presentation, I hope to alleviate some of your fears and give you some concrete suggestions and methodology to do well in your Math for Meds test, but even more importantly, in your practice. So let's go forward. In 201 and 202, we advocate using dimensional analysis approach. Now, if this causes you any concern because you used formula, well, I just want you to, take a deep breath and go forward and take a listen to this approach. We find that this one-stop method works for all areas of your medication calculation needs. And so that's important. You won't lose it. Memorization of formulas can be lost with time. If you don't go to a certain area, you may forget it. You may say, "Oh, I'm going to stick with one area or one place," and you may think so now, but there's so many opportunities, and you may change over time. I know I did. And one of the important things that I learned is dimensional analysis can be used for any type of math calculation. It's the same principles and the same process that you do. So it really is a one size fits all, and that's important. So you won't lose it if you don't use it. So that helps with your safety. So let's go forward. Open your mind, see what you think again by looking at this approach, and hopefully it will be beneficial to you as you go forward. I'm going to begin with just an overview of dimensional analysis as we will use it. And basically, what we're going to be doing is creating an equation from the prescription and the medication on hand. We use a concept called same dimensional principle, and it may be called something more lofty, but that's what I use, same dimension principles, which we'll talk about a little bit further. We develop fractions and arrange these so that it leads to a factor label that represents the answer or a unit of measure. So I'm going to use the term factor label because this is actually called factor label um, problem solver. So when we have factor labels, these are the unit of measures that nurses need. For instance, mils per hour and so forth. And then we apply all of these properties and solve that equation. So it really is a four-step situation, and it's pretty easy once we get along and identify those principles that are important and just really some steps that we can do consistently. And when we do those steps consistently, it just becomes easier and easier. So let's take a look at some foundational knowledge that you already have. And this is just to remember that whole numbers can be written as a fraction. So, for instance, 100 can be written as 100 over 1. When you are considering a fraction, remember that the top number is a numerator and the bottom is a denominator. So let's take a look at what I mean by same dimension. Same dimension, a principle, is when we are creating this equation. We can look at the prescription and on hand and develop an equation whereby we can represent the prescription as 5 micrograms over 1 minute or 1 minute over 5 micrograms. So either of these are correct. The same example is seen here. The on-hand prescription, on-hand medication can show 2 milligrams per mil on the bottle, for instance, and we can write the equation and represent this as 2 milligrams per 1 mil or 1 mil over 2 milligrams. And either are correct. And how we determine which goes where is really, again, about solving for that factor label. And we'll take a look at that more in subsequent slides. So, what guides this same dimensional principle, like in terms of our decision to put something in the numerator versus the denominator? Well, it comes down to this idea of a factor label. And that's why it's so appropriate that we use dimensional analysis because we're always solving for a unit of measure. for instance, mil per hour, drops per minute, grams, tabs per day. These can also be considered factor labels. And so I'll be using going forward that concept of factor labels. I'll use that term throughout, okay? So we will be solving for one of these. And so accordingly, we'll develop an equation and we'll go further and I'm going to show you how this can be applied. Other foundational information. Once we have our fractions and we develop an equation, these principles come into play. Recall that you can cross cancel like terms. And when I say like terms, I'm referring to factor labels. However, there's a certain couple of things that you need to recall. You can cross cancel like terms if they're opposite the multiplication and if they're opposite the position. So, what does that mean? So, let's take a look. I have 100 mil over 60 minutes. I notice on the opposite side of this multiplication, I have minutes in the numerator here. So I can cross cancel these. That's a principle of math. So when I do that, I'm left with the factor label mil. And that works in this particular case because I'm solving for mils. And we'll integrate all of these together and do many problems so you see what I mean. But that's an important concept. We can cross cancel terms, i.e., factor labels, if they're opposite the multiplication sign and opposite the position. A numerator cancels with the denominator. When we are solving for our multiplication fraction equation, the next step we'll do is after we cancel, we'll be multiplying the fraction straight across, first with the numerator. So in this case, you see it was 100 times 30, and that gives me 3,000. Then what I'll do is multiply the fraction straight across the denominator. So that would be 60 times 1 gives me 60. And the next step in that solving of that fraction multiplication equation would be to divide the denominator into the numerator. And you can see here when I did that, it leaves me with 50. And because of all of these being canceled, I technically have 50 mLs because that's the factor label left. We'll take a look at this further and integrate all these steps. The last principle that we'll be using in our equations and solving for equations is this idea that we can use conversions to cancel like terms or like factor labels. So what does this mean? I'm just going to give you a brief understanding of it in this slide. Let's say, for example, that we need to solve and find out how fast to run a pump in mils per hour. However, a prescription is written and we have a prescription that says 100 mils over 60 minutes. The problem with that is there's not a like term. See, there's a dissonance between what we really need, which is mils per hour. However, my conversions that I memorize helps me to cancel out these terms so I can have hours. And these need to be conversions that are equivalency. So they're equivalency. So how does this look? I have 100 mils per 60 minutes. I want this to be mils per hour. So I recall that 60 minutes equals 1 hour. And I create a fraction accordingly, where I have 60 minutes in the numerator and 1 hour in the denominator. And that's purposely done in this way so that I can cross cancel the minutes. And when I do that, I'm left with mils in the numerator and an hour in the denominator. So that means that I will get and be able to solve for mils per hour accordingly. So let's take a look as we go forward as to important conversions that you should remember. Here we have some common conversion principles that or equivalents that I mentioned that would be used in the second level. So many of these I'm sure you already recall, and if not, just brush up on them. These are things that you should just keep in your foundation of knowledge, okay? Here are some other common metric measures that you'll be using in Nursing 201. Again, it's a memory thing. There's certain things that we do have to memorize because they're very foundational so that you can apply them effectively. So again, same concept as I mentioned, these would be useful as conversion factors. And let's take a look at this. So if we had, for instance, a 1,000 grams, we could write this as 1,000 grams over 1 kilogram. Okay, so that's how we would put this in our equation. Or using same dimensional principle, I could have put this in my equation as 1 kilogram over 1,000 grams, depending on what I'm solving for. So I would memorize these as well if you don't already have that in your, um, gray matter somewhere. So the final thing that we'll talk about a little bit is the foundational concept of rounding. I'm not going into how one would round. I think that's a very basic concept also. And it's really important to just refresh those concepts if you're not sure. There's some great videos on the internet about that concept. So I would direct you there. For our purposes for testing, most of the problems we will ask that you round to the nearest tenth. And this would be for most everything. And we'll be very specific on the test. So I will have the rounding rules posted in the direction. So I don't want you to, get too alarmed. But I think these is so general that you already have these in your foundation of knowledge. As you know, if you were administering a medication, you can't administer parts of a drop or parts of a capsule. So in those cases, we would always round to the nearest whole number. An important safety concept is handling zeros. We know that we don't have any trailing zeros. And there's an example here. For instance, if you get a result from your calculator is 3.0, we know that the point zero means nothing, in that, and it's really just a whole number 3. So we'll remove that when you put your number in your test. Leading zeros, remember also that that's important if you have a decimal number. So you always need a preceding zero. So we can differentiate that from a whole number. So that's very important. And you know that this is related to the administration of medications and preventing errors. I just want to put a little bit more emphasis on the concept of the zeros and how you transcribe your medications because this is important to safety. So, to reiterate, do not use a trailing zero after a whole number. And here we have that example. But remember to use a leading zero for all doses less than a whole number, which, for example, would be 0.2 mils. Okay, so again, reiterate the safety factor and the transcription of this is very important. So let's try to integrate all of the concepts together, and we'll try to do this very systematically. We always begin with our prescription. So let's say the healthcare provider orders digoxin 0.125 milligrams PO daily. You're ready to give this medication, and you go to your Pyxis, and you see that they have a 125 micrograms per tablet. Now, right away, I'm hoping that you maintain your 5 rights. That's very important. If you don't see that micrograms are not milligrams, then you will give this, and it will be a very serious problem. So let's figure out what we do need to get. So you begin with your factor label. So what you are trying to figure out is how many tablets do you give per day. So I always write on the left side the thing that I need to solve for, the factor label that I'm solving for, and that will help direct my equation and how I arrange my fractions. So tabs per day. So now it's time to begin your fractions. and making your equation. So right away, you start with your prescription, and I have a prescription of digoxin 0.125 milligrams per day. So right away, when I see per day, I look back to my factor label and recognize that I want a day to be in the denominator. So I am going to purposely arrange my fraction thus. So I have 0.125 milligrams per day. So that starts my process. So I'm in the right direction. However, I do know I need to have a tab in the numerator. So let's look to see what you have within your problem. And I have that digoxin 125 micrograms per tablet. So right away, I key into this tablet and I remember that I have to have a tablet in the numerator. So because I do, I need to purposely create my fraction whereby this tab is in the numerator per that same dimensional principle that we talked about. So see, I have here one tab over 125 micrograms. So this means I'm in the right direction. I have the tab in the numerator and the day in the denominator. However, what I do also see is that I have micrograms and milligrams here. Now, you need to be able to cancel out all these other factor labels if that does not apply to this particular problem. So we only need to have tabs per day left. And if we have other factor labels, you need to use your conversions. And so this is why remembering your conversions from the previous slides will be very useful. So I know 1,000 micrograms equals 1 milligram. So I'm going to purposely create a fraction whereby I can cancel out these terms. And remember, it's a cross cancellation. So let's take a look at how I do it. Hopefully you recognize that we're going to put the micrograms in the numerator because I see this cross cancellation possibility. And I also see the milligrams down here in the denominator would work very effectively to cross cancel that from this first milligram. So let's see how we do this. So we take the milligrams, we cancel that out with the milligrams. The micrograms cancel and the micrograms cancel. You're left with tabs per day. This means your equation is appropriately applied. Now, these red marks will disappear, so keep this in mind. Write it down on your paper as well so we can keep the process going. Now, once you cross cancel, the next step, as we talked about in the previous slide, is to use the principle of fraction multiplication. So that means we're going to go across in the numerator and simply multiply. And we're getting our calculators up, so you can do this with me. 0.125 times 1 times 1,000 micrograms gives me 125. We're going to do the same here as we move across in the denominator. 1 times 125 times 1 gives me 125. So we had left with 125 over 125. And your properties of fraction, you should know that anything over the same number equals 1. And so we have 1 tab per day. And that is your answer. Now let's practice some more typical problems that you may see on a Nursing 201 exam or perhaps in your nursing practice in MedSurg. We begin always with the prescription, and let's read what we need. And we're having a prescription here for atropine 0.5 milligrams IM stat. So the question is, how many milliliters will the nurse administer? So when I get something like 0.25 milligrams IM stat, we don't know we need milliliters, right? What we have to do is to see what's on hand. And so I have an example here of a label, a bottle that you would be drawing this medication from. And we would just look at the label and recognize that it comes in milliliters, right? That there's a concentration of medication in this bottle, and we will get 400 micrograms per mil. They already did some of the math here and conversions, and we have it 0.4 milligrams per mil. Now we could ideally take this one. However, I'm going to use this just to show you how to do conversion factors, and that's important to keep practicing and understanding. So, having done so, let's see how we're going to manage this. I begin with my prescription, atropine 0.5 milligrams, and I am going to just create a fraction with 0.5 milligrams on top with 1. I'm not sure how this is going to work because I'm really looking for mils, and I'm not sure how that's going to factor in. Sometimes when I put something down in a fraction form, I might have to inverse it so it works with my equation. And sometimes I don't see it right away, so don't worry if you don't. The idea is that once you create that equation, you start to cancel out those terms, and then you go, oh, wait, it's not working. I need to flip this. That's okay. It's a process, and sometimes you can see the patterns right away, and sometimes you can't. So just understand it's part of the part of what you may have to do, and that's okay. So again, I'm going to work with this 400 micrograms per mil. So that's important for me because I know my mils. That is what I'm trying to solve for, my factor labels. So that's going to be important. So to have this, we would need to make sure that would be in the numerator. So I'm going to apply that effectively in this fraction with 1 mil in the numerator over 400 micrograms. Now, as we know, and we talked about, this is great that we have the mils here, but I don't want any of these other factor labels. So in order to take care of removing those, I have to use the principles of canceling, and then particularly with conversion factors. And so we know 1 milligram equals 1,000 micrograms. How I determine how I create this fraction is dependent on where I want to cancel and what I want to cancel. So just very quickly, I can see that my micrograms are in my denominator. So for the rules of cancellation and fractions, I would have to put that in the numerator. And so that works because I also have milligrams in the numerator, and therefore I would want this on the other side to be in the denominator. So with that intended, let's see, we put milligrams and milligrams, micrograms and micrograms, leaving only milliliters. So I'm on the right track. So this equation is okay. We're going to go and continue the principles of fractions and multiplication, and we will go and multiply the numerators. 0.5 milligrams, 0.5, forget the milligrams, right? 0.5, 1 times 1,000, and that gives me 500. We're going to do the same to the denominators. 1 times 400 times 1 gives me 400. So we have 500 over 400. And if you did the division, which we divide, right, the denominator into the numerator, we get a answer of 1.25. And we have mils, so that is the answer. We have here another example, very basic IV calculation. And let's read this healthcare provider order. It says 1,000 cc's of LR at 12 hours. First of all, I don't really like this at 12 hours. If we were to write this down, a prescription should say every 12 hours. That would be most appropriate. The other thing I want to bring attention to is this idea of CC, 1,000 cc's. As you know from your metric equivalencies, that there's a one-to-one relationship between mils and cc's. So I don't really need a conversion. In my mind, I know that 1,000 cc's is the same as mils. And that's important for me because I am going to have to program this pump, and the rate is always most likely in mils per hours. Most pumps are mils per hour. I can't say absolutely all the time because there's always different, things that go on. And so an absolute is very hard to define. I never like to say absolutely, but most of the time you're going to do mils per hour. So I know my equation needs to follow suit and have mils in the numerator and hours in the denominator. So let's go back to our order. That's all we have here. And let's see if this is enough or if we need conversion factor. So my order is 1,000 mils and every 12 hours. So that's awesome because that is all I need. I know I can put the 1,000 mils as the numerator, which is consistent with my factor label, and the 12 hours in the denominator. So I have the correct equation. I have to do nothing more except, because there's no multiplication, I'm just going to do that last step, which would be to divide it, right? So if you divided 12 into 1,000, you would get 83.33333, right? So if we do our rounding rules, we know we're looking at the hundredths and it's less than 5. And so I'm just going to simply remove everything to the right. And so it's 83.3 mils per hour. Let's take a look at another order for an IV. We have a potassium order for 40 milliequivalents in 200 mils of normal saline. The policy states to run this at a rate of 20 milliequivalents per hour. So what rate will the nurse program the pump? And as I mentioned, pumps are usually in mils per hour. So that's going to be our factor label. When we're looking at potassium, it's a high risk medication. And so it's very important to look at the safe rate of administration when you're doing these medications. So we're going simply through math, but we have to recognize the importance of looking at all your math problems when you're in the practice setting and looking at your medications and really identifying all those important variables about compatibility, right? Is it compatible? How do you run it? Is it a piggyback? Is that appropriate in this case? What is your outcome? What are you looking to do? And what is the safe rate of administration and your safe doses? So pumps are awesome because pumps are mostly smart nowadays. I don't think there's any place that you'll go where they're not smart. And smart pumps give a program specifically for that institution in safe doses. So a lot of the math can sometimes be done for you, but that doesn't make you not responsible, because if you don't know how to do these things effectively and completely, then you will sometimes may be faced with a program pump that has been defective. It's happened. There's sometimes you have to be able to confirm. So understanding how things operate are very essential. So now let's just go back to the concept of math and simply math medication administration and how you derive your mils per hour. So this is our factor label. So I am going to recognize that my arrangement of fractions have to be done so that the mils would be in the numerator and the hour would be in the denominator. So let's see what we have to work with. We start with our provider order, our prescription, 40 milliequivalents in 200 mils. So I like this right away, and I see the mils that I need to have in my numerator. So I will write my first fraction accordingly as 200 mils per 40 milliequivalents. Now, I like the mils in the numerator. I do not like milliequivalents, so I'm going to look to see what else I can do to get rid of that, cancel that. And it works out really nicely in this particular case because I have a potassium rate of 20 milliequivalents per hour. So I see right away that hour is important to my answer, right? I need that hour in the denominator. And a great piece of this is that I have a 20 milliequivalent. So right away, I know that's going to help in my cancellation. So I write this accordingly as the fraction 20 milliequivalent. When we have this done, we have this cancellation that we can do of the milliequivalents. And this leaves me with my mils in the numerator and my hours in the denominator. And that means my equation has been arranged correctly. And so now it just is the next step we do when we do the numerators, and we're multiplying them accordingly. 200 times 20 gives us 4,000. And then we do the like manner in the denominator. 40 times 1 gives us a 40. So then we do our division. So we're going to divide 40 into 4,000. And then what that leaves us is with a answer of 100. And so the answer would be 100 mils per hour. So here we have a problem with an IV gravity. And it is about, we're going to give famotidine 20 milligrams IV, and that's in 100 mils of normal saline daily. We know it needs to be administered over 30 minutes. The drop factor is 10 drops per mil, and the question is how many drops per minute will the nurse run the IV? So we are looking to solve for drops per minute, and that's how we set up our equation. The important piece of this order is the 100 mils because if you consider it, this medication has been placed within that 100 mils, so it becomes non-essential to the administration time. So it'd be 100 mils, and I put that over 30 minutes. So when you have this set up as such, we're already working towards getting our minutes in the denominator. Now we need to get rid of mils and we need to get drops in that equation so we can solve correctly. So we do know the drop factor is 10 drops per mil. And so the drops will be in the numerator and I put the mils in the denominator. And this way I can cross cancel and do my math. So when I do that, I see that we are left with drops per minute. So my equation is correct. When we do the math going across the multiplication, we are left with 1,000. And then we have that over 30 minutes because then we do our denominator. And then when we do our division of the denominator into the numerator, we are left with 33, point 3. Now the answer, because this is a IV that is per gravity, we have to consider that we can't give this as a decimal, right? There's no parts. So the answer would be 33. Now, let's take a look at another problem where the concentration of medication is not as relevant because we have the administration here. And the rate of administration and what is the order is really 250 mils to be infused over 2 hours. And within that 250 mils, we do have, of course, the medication concentration there. But that is not necessary to understand the rate. So we are solving for mils per hour. And take a look at what you have here. Simply 250 mils, which would be correct for a numerator, and then the hours would be in the denominator. And so when you see that, you know you have all you need for this particular problem. And so you do your division, and when you do that division, you would have 250 divided by 2, and you would have this as a rate of 125 mils. Oops, let me write that 5 as best I can, mils per hour. So here we have a more complex problem whereby the concentration of a medication becomes important to the resolution or solving of the equation. So, and the reason why I know that is because the order identifies a concentration. So the order is a 2 milligrams per minute. So that kind of gears me into that the rate of administration and the concentration become significant. So I'm going to start with trying to solve for this problem. I'm going to be solving for mils per hour. I'm going to put my prescription as 2 milligrams per minute in this fashion with the 2 milligrams in the numerator per minute. Not quite sure how that's going to pan out in the resolution of this, but I start that way and then I begin to formulate my equation. And if I have to make any inversions, I can do so. But I think that's a good place to start typically. The next part of this problem is the concentration is 2 grams in 500 mils. Unlike the last two problems, this becomes important once again because my prescription requires some kind of concentration. So that kind of gears me into that this is important. So I'm going to put the 2 grams in the denominator, and I'm going to put the mils 500 in the numerator. And the reason for that is I'm working towards this mils per hour. Now, having done this, I still have a mill, but I have too many things that I don't need, the milligrams, the minutes, and the grams. So I'm going to begin to consider my conversions and to get rid of that. So I understand that a conversion 1 gram equals 1,000 milligrams, and another conversion that's going to be important is the 60 minutes equals 1 hour. I still need that hour, so that's important to be placed in my denominator. So whichever one you do first, it doesn't really matter. Just it's your system of how you want to do it. But I like to put down the prescription sometimes, and then everything I have in the problem, and then add my conversions. Some people work quickly and they like to put conversions right after, you know, the beginning or closer to the end. They like to do the 60 minutes first, or however you do your conversions, it doesn't matter because it all works the same way. So I'm going to start with 1 gram equals 1,000 milligrams, creating my fraction whereby the gram is in the numerator and the 1,000 milligrams is in the denominator. And that placement is to gear me into this cancellation of that term milligrams. However, that leaves me with mils, grams, and minutes. So I want to get rid of this grams, and that works as well. So by placing this 1 gram in the numerator, that also cancels this 2 grams. So that's great. So I'm left with mils per minute. So I want to convert that, right? I want in mils per hour. So what will happen is I'll use my next conversion, 60 minutes equals 1 hour. I purposely place my 60 minutes in the numerator with the intention of canceling this last factor that I don't need. And I have my 1 hour in the numerator. So that is important because you start to get a sense that everything is all set, because now we only have mils per hour. And then we do our directional um, multiplication, right, of the numerator. And bear with me as I'm going to do this with you, and you can look at your own calculator, put it on pause to see what you get. So it's going to be 2 times 500 times 1 times 60, and that gave me 60,000. And then you have 2 times 1,000 times 1 equals 2,000 in the denominator. So when you do that, you had 60 in the numerator, right? And I'm going to just do that as best I can. And then I have that under 2,000. And what will happen is I'm going to do that. I'm going to divide the 2,000 into the numerator. And I have a result of 30 mils per hour. Okay, so let's try another one. This time we're looking for units per hour, which is very typical of many of the patients you may come across who are having heparin for whatever reason. And so this particular patient has a pulmonary embolism, and we're going to have a prescription of 15 mils per hour. That should be the infusion rate. So we start out with knowing our factor label as units in the numerator and hours in the denominator. So this 15 mils per hour, I will write accordingly so that my hours remain in the denominator. So that's great. So now I need to find units. And so I find it here with that which is on hand. This is actually the bag of heparin that you have on hand. When you look at the heparin, you will see this concentration. And there may be very different concentrations. So it's very important to look at your bag when you are actually doing this in practice. So I know I want 25,000 units as a numerator, and then I can put my 500 mils in the denominator. And so when I do that, I see that I have a correct equation for this answer, because once I cross cancel, I'm left with units per hour. So that means this equation is right. So now it's just simply doing the math, multiplying the numerators and then the denominator, and then dividing it. So let's try to do this. And I get 15 times 25,000 gives us, and again, we have to be careful with this. I think it's 307,500,0. And let me make sure I did that correctly. 00, yeah. And then that would be over 500. And so let's do the math on that. So let's see what you get. And so when I divide it by the 500, I get 750 units per hour. Now here we're looking at a little bit more involved. We are looking at some more conversion factors. And when you see things like nitro and things, these are more critical care in nature. So they become a little bit more, I guess longer is the word, not necessarily complex, because as long as you're doing your dimensional analysis in the same way that you do it, it seems the same concept. It's just a lot more numbers. And so you have to be careful. I'm one of those people that I'm not very detailed, and damn, I make mistakes with these zeros. So for me, I know I have to check things at least twice to be sure I'm transcribing them effectively. So let's take a look at what we have here. We have an order for nitro at 10 micrograms per minute. The concentration of nitro is 100 milligrams in 500 mils. How many mils per hour should the nurse program the pump? So let's start with our prescription of 10 micrograms per minute. Now I'm going to solve for mils per hour. So I'm not sure how this is going to work out. So I'm just going to put it down as 10 micros per minute and see what happens and see if this is going to work. As I said earlier, it may be that it's not the right place until I see the whole piece of my problem. And so I'm going to start again. So I'm going to do the one on hand, and I get 100 milligrams in 500 mils. So this helps me because I know I need these 500 mils in my numerator. So because of that, I'm going to put the 5 mils in my numerator, and I have 100 micrograms. So that's actually working out. I can tell already it's going to work out, but let's see how I can make it work out using conversion factors. So we need to get rid of minutes, right? We want hours. So how do we get hours in the denominator and get rid of this minute in the denominator? So I use a conversion factor, 60 minutes over 1 hour. So this is great because I finally get this important piece that I need in my label, factor label answer. And so I think that's going to work. And now I still have to get rid of micrograms and milligrams because I only want mils and per hour. So then I will use my other conversion factor, and I know 1 milligram equals 1,000 micrograms. And so let's put that in the order that will help cross cancellation. So as you can see here, I put 1 milligram in the numerator over 1 microgram purposely so I can get rid of all of these other labels I don't need, these factor labels. So let's see this very quickly. Of course, it'll disappear, but you get the idea. 10 with the micrograms here in the numerator, I can cancel out with the denominator. I'm going to cancel out the minutes in this denominator with this in the numerator. I'm going to get rid of the milligrams in the denominator with this one in the numerator. I'm left with mils, and I have an hour, so this is correct. So that's important to know. Now it's just a matter of doing your math, your numerator, your multiplication across all the numerators, then your denominators, you're going to multiply them, and then you're going to divide the denominator into the numerator to get your answer. So let's do some of the math, and you'll do this as well with me. So 10 times 500 times 60 equals, I have 300,000. And let's write that out quickly. It will disappear, so you can do it on your own and check back. And then we're going to go and divide it by 100 times 1,000. And so if you add those two zeros, I get 100,000. So if I do that, I'm going to divide it by 1, 2, 3, 4, 5. and that should give me 3. And that makes sense to me because typically when you're dealing with um, nitro and micrograms per minute, you're doing a very low rate. So if it's a high rate, I start to wonder I might have screwed up. So just a heads up on that. Dopamine, nitro, stuff like that, that can be, it should be very small typically. So when I get that, I have 3 mils per hour. Okay, so we have our last problem here, and it can look complicated when you're looking at critical care types of IVs, but in effect, it really is the same process. And as long as you don't lose track of things, you're going to be fine. It's really applying the principles and solving for mils per hour, setting up an equation to this end. So let's start with our order at 5 micrograms per kilograms per minute. I'm going to begin with the 5 mic in the numerator and the kils per minute in the denominator. And that's typically how you see these kinds of IVs equations starting. On occasion, this may be incorrect and you might have to flip things around to solve for your particular factor label. But this is a great way to start. And if I had to make some modifications and move and flip things around in my fractions, then you can do so. Just so you know, you need to be left with just a mils per hour after canceling all these terms. Then I'm going to move to the dopamine, 2 grams per in 250 mils. Now, in previous ones, particularly comes to mind that drop per minute problem. We did not look at the concentration. But in this case, I am. And the rationale for that is I see a microgram in my um, order, and there's a relationship with the mics and the grams. And I can see quickly that that's important in the conversion of and cross canceling situation. So I'm going to do it like so. Sometimes I'm wrong and I don't need that, but you'll see right away there's a relationship. So I'm putting the mils in the numerator to solve for my factor label. I'm going to put the 2 grams here. Now, of course, we have a relationship, but I understand the principle of conversions, and I know that both of those were important, so I can cancel them out, and I can do that with a conversion. So we remember our conversion 1 gram equals 1 million micrograms. So I write that accordingly with the grams in the numerator and the denominator has the micrograms, and that's set up accordingly so that I can cross cancel these terms that I don't need, and I know I'm on the right path here. Now I have mils, but I still have kilograms per minute that I need to remove by cross canceling. So I go back to my equation and see this patient weighs 85 kilograms, and that's important to my equation. I'm going to put this in the numerator so that I can cancel that out so I know this is correctly applied. And now I see when at this point that everything would have been canceled out except I have mils per minute, and I need to make this as a mils per hour. And that brings me to that idea of conversion. So I want to change that to an hour. And to do so, I will use that principle. I put the 60 minutes in the numerator, and then I have that over 1 hour. And now I'm correct. So let's do all of this to see if we cancel all our terms and see if we set up our equation correctly. So micrograms, I cross with micrograms. I do the kilograms with the kilograms. I do the minute with the minute. I do the grams with the grams. And I'm left with mils and I'm left with hours. So that's correct. So now it's just a matter of multiplying and your numerator. And when you do that, I have 6,375. And when I do, and I apologize for how this looks. And then if you do the denominator, you get 2 million. And when you divide the 2 million into the 6,375, I came up with 3.1 8, 7. And when we want the rounding rules for testing purposes would be to the 10th. So that would be 3.2 because I'm going to round up because it's an 8 here. And that would be your answer. So this concludes the presentation, and I hope this was useful for you. And those of you who may not have liked dimensional analysis, maybe you can see some benefit to it. And those who are a little bit rusty, just take this opportunity to continue to practice those different types of problems that you see. Ogden is great. Review those chapters accordingly. Particularly 16 and 17 may be new, and so I would ask you to take a peek at that. And those are critical care types of problems. We will not have any obstetrics or pediatrics on this exam. We do have your math packet also posted, and those are just some exemplars of types of problems you may see when you are in your practice and also on the NUR 201 exam. Please defer all your questions until the course starts, and that will be in the fall. The answers to that math packet will also be posted to your course. So I look forward to meeting you all, and enjoy the rest of your summer, and thank you for your attention.